8, sorry, it's less than 8, not 7. All right, the other day we went over solubility, we went over terminology like, the solvent is the thing that's doing the dissolving, the solute is the thing that's getting dissolved, okay? We talked about what a precipitate is. A precipitate's a solid that forms and settles to the bottom and is insoluble, which means it doesn't dissolve, okay? We talked about some things that can affect solubility like temperature, agitation, okay, things like that. And then we went over this chart, the solubility chart, and we went over how to use it, okay? And we said that if you're given a compound, like let's say you're given, let's say sodium phosphates, okay? So that would be Na2PO4, I think, okay? So we get that, okay? I look up PO4, sorry, it's Na3, no, okay? I look up PO4 here it is, and then anything it's with that's in the first row is soluble, okay? Anything it's with in the second row is not soluble. So obviously sodium phosphate then is soluble because it's in that row, whereas if I had something like this, sorry, Cu, copper 1, okay? I would look up iodine, it says it's soluble with most things, but not with copper when it has a 1+ charge. Just a minute. No, just a minute. Okay? Does everybody follow there? Okay, ringing a bell? All right. Okay, so we're going to move on to now is, okay, what a polar molecule is or what that means. Okay, the example that we're going to use is water. Water is the most common thing around, at least for us. Okay, and it's a polar molecule. It's the fact that it's a polar molecule affects how a lot of living organisms do their thing. Okay, that is especially for plants. Okay, how they transport water, how plants transport water is entirely dependent on the fact that water is a polar molecule. Okay, if it wasn't, plants wouldn't be able to transport water the way they do. Okay, photosynthesis would then work a lot differently. Okay. If you had some animals depend on the polar nature of water in order to survive. For example, if you've ever seen the little water striders, okay, that sit on the water, right? They got their legs kind of spread out like this, and they just float kind of on the surface film. Okay, well they can only do that because water is polar and there's surface tension. Without water being a polar molecule, there'd be no such thing as surface tension. Okay? It just wouldn't exist. So lots of things depend on the fact that water is a polar molecule. Water being a polar molecule makes it do a lot of weird things too. Okay, most things when you cool them off, they contract, they get smaller. Okay, what does water do when it freezes? It expands. Okay, that's why if you ever put a water bottle in the freezer, okay, the bottom pops out. Right? You never have a water bottle or anything that contains fluid, okay, mostly water, okay, that's filled all the way to the top. There has to be room for expansion because if it freezes, it'll shatter or crack or whatever the container. Okay, so you can't. You always have to be mindful of the fact that water is going to expand. Okay, and that's because it's a polar molecule. All right. So what is a polar molecule? This is something you really need to know. Okay, what does it mean to be polar? Because I'm going to ask this on a quiz, on a unit exam. Okay, crucial that we know what it is. Anything that's polar has an unequal distribution of charges. Okay, what that means in English is one side of the molecule is negative and one side of the molecule is positive. Even though the charges are balanced, one side of the molecule ends up being more negative than the other side. Okay? And that's because the electrons, while they're being shared, are not being shared equally. Okay? So in water, we've got 2 hydrogens and we've got 1 oxygen. Okay, so the 2 hydrogens are these little pluses up top here. This is a proton, this is a proton. Okay, so that's the nucleus. Okay, this is the nucleus, that's the nucleus of the 2 hydrogen atoms. Each hydrogen atom has 1 electron, and it's supposed to orbit hydrogen like this. Okay, when it bonds to oxygen, this becomes a molecular compound, not an ionic one. Okay, so water is molecular. Okay, and so as a result, these are what we call covalent bonds. That is, the electron is being shared in 2 valences, covalent. Okay, a valence is anywhere where you can find an electron. All right, so the electron's being shared between this hydrogen and this oxygen. But here's the problem. Hydrogen can't hold on to its electrons nearly as well as oxygen can. It's something called electronegativity. If you pull out your periodic table, okay, each square, each element square, has got a few different kinds of numbers in it, okay? And one of the numbers, and I think it's in the top right on your guys' periodic table. No, sorry. It's right under, it's the small number underneath the atomic number. It says electronegativity. Okay? So if you look at oxygen, oxygen's electronegativity is 3.4, which is quite high. Okay? Whereas hydrogen's electronegativity is 2.2, which is low to moderate. Okay? Most metals have very low electronegativities. You can see like lithium is 1, sodium is 0.9. Okay? They don't hold on to their electrons very well. They just give them away. Okay? Well, oxygen, on the other hand, holds onto electrons very tightly. Okay? So what ends up happening is when it's sharing, and I say sharing like this with quotations, okay, this electron, it's not really sharing it, it's getting it more often than the hydrogen atom is. So instead of the orbit of this electron looking nice and circular, the orbit of this electron now ends up looking like this. Okay, it spends very little time near the hydrogen atom and a lot of time near the nucleus of the oxygen atom. Okay, what that ends up doing is essentially leaving two protons, which are positively charged, essentially exposed at the top of this molecule. Meanwhile, all these electrons are all hanging out down here. Okay, and so this end of the molecule ends up being very negative. Okay, so we end up getting a negative charge down here and two positive charges up top. Okay? It's polar. It has like a positive pole and a negative pole. Same way the Earth has a north pole and a south pole. Okay? Hence the name polar molecule. So you're a polar molecule if your electrons are not being shared equally. Okay? They're ending up in one place more than the other. So the atom becomes charged at the ends. Okay? That's what it means to be polar. Okay, questions on that? All right, so that's kind of what's being explained here. Okay, so sharing's not always equal. Okay, some elements are more electronegative than others. Okay, and so they attract the shared electrons more than the other element. Okay, that is what is called a polar covalent bond. Okay, now here's what that leads to. If you have one end of a molecule that's positively charged, and you got a whole bunch of other molecules around that are similar to it that have positive and negative ends, could they be attracted to each other now? Opposites attract, right? Okay, so what ends up going on is the positive ends of water molecules, so let's say like this one right here, is attracted to the negative end of another water molecule. And they'll form what's called a hydrogen bond. It's a weak bond that forms between the two. This is the bond that's responsible for surface tension. Okay? You get surface tension because weak hydrogen bonds get formed between a whole bunch of water molecules. Okay? Can you break that surface tension easily? Yes. Does it reform easily? Yes. Okay? Hydrogen bonds are like that. They can form that bond, but it's broken, but it goes right back again. Okay? That's what a hydrogen bond will do, right? So they'll be attracted to each other and they'll form these bonds. One water molecule can form 4 hydrogen bonds, right? It can form a hydrogen bond, okay, with each of its hydrogens, and it's got 2 spots at the bottom that are negative. So other water molecules will hydrogen bond to those spots. Okay? So one water molecule could be attached or hydrogen bonded to 4 others. Right? And that creates kind of a net, okay, or a film on the top of the water. Okay? Everybody with me there? All right, so that's why water tends to kind of bubble. Like if you get just a little droplet, okay, like on the leaf of a plant or something like that, it forms kind of a round kind of drop on there. Why it even makes drops at all and doesn't just fall in sheets, okay? It's because of this hydrogen bonding and this surface tension. Okay, are there other molecules in nature that could be polar? Yeah, there are, okay? Lots of them, in fact. And what that can mean is that water could form hydrogen bonds with other polar molecules as well. I mean, this hydrogen doesn't know, it's just attracted to things that are negative. It's positive, it likes things that are negative, okay? It sees them as like, hey, okay? That's it, you know, and it goes after them. Okay, everybody with me there? You guys understand how that works? Okay. All right, so we got our hydrogen bonds forming here. Like we said, we can form, one water molecule can form 4 hydrogen bonds. Okay, the angle of those bonds ends up being about 90 degrees. It forms pretty much a right angle. Okay, the 2 hydrogens are spread out by about 90 degrees at the top. Okay, which of course then gives us the 2 negative spots as well being about 90 degrees apart at the bottom. Okay, so it can form a fairly symmetrical shape, okay, when it's making hydrogen bonds, right? Which is why we get crystals for snow. Okay, as the water begins to cool as a liquid, okay, it contracts, but it can only contract so far before we start getting these positives and negatives getting too close to each other. Okay, if we start getting water too close to each other, okay, then the positive or the like charges will repel. Okay, and that happens right before it freezes. Okay, water is most dense at about 4 degrees Celsius. Okay, then below that it starts to push back. Okay, water begins to expand again. Okay, and then when it freezes, it kind of pops open, right? And that's why ice floats on water. Okay, I mean, you probably don't think about that all that often, but the reason ice floats on water is because it's less dense. The molecules are further apart. Okay, if it wasn't that way, lakes would freeze from the bottom up, and that would be weird. Yeah. No, yeah, that's right. No fish would live. You'd have anchor ice, okay? No hockey, no curling, no any other ice sports, okay? Those would all be gone unless you live somewhere where it was actually cold enough to freeze the entire lake solid from the bottom, okay? It just wouldn't happen that way, all right? Well, actually, it would be easier because it probably would be less likely to freeze all the way from the bottom. There would always be liquid on the top. Yeah, but really cold, right? Okay. So here's what happens, this is what I was just explaining here. Liquid water, okay, around 4 degrees Celsius, okay, has the water molecules, you know, not tightly packed, but close together. Okay, they can still switch places because it's a liquid. But once it freezes, okay, they form these hydrogen bonds and they form a crystal matrix, which is why water looks crystalline and why we get snowflakes and things like that. Okay, so they form like that. Okay, they create a distance between themselves because of this repulsion of like charges, and the ice ends up being less dense. Now, that crystal shape is fairly, let's say, fractal, okay, which means that it's different every time it happens. No 2 snowflakes are the same, okay, so it's slightly different every single time. Okay. All right, and we said before that any polar molecules can form hydrogen bonds with each other, right? So ammonia is a polar molecule. Okay, it can form a hydrogen bond with water. Okay, lots of things can do that. Okay, so make sure you understand. Okay, hydrogen bonding is also an important part of talking about what polar molecules can do. Those hydrogen bonds are important because they're going to produce a couple of the behaviors that water exhibits. Okay, those 2 behaviors are called cohesion and adhesion, which we'll talk about here in just a minute. Okay, cohesion means water sticks to itself, surface tension. Okay, adhesion means it sticks to other polar things. Okay, so you may have seen if you have like a really cold drink in a glass, that you get condensation on the outside of the glass. Okay, but sometimes those water drops don't run down the side of the glass right away. They can actually almost defy gravity and stick to the side of the glass. You guys seen that? Okay, that's because of hydrogen bonds between the water and the glass. Okay, until the water gets so big that the hydrogen bonds aren't strong enough to suspend that water droplet anymore, okay, it'll stay there. When it gets too big, the hydrogen bonds break and it slides down the side of the glass. Okay, so hydrogen bonds can be reasonably strong, okay, until something disrupts them. Then they reform again. Okay, trees use this property of water in order to transport water up the trunk. Okay. Some plants, some trees are really tall, okay, over 100 meters. I mean, if you're looking at like giant sequoias and things like that, they can be really, really big. So you got to move water a long way, and you got to move a lot of water. Okay. Is water heavy? It is. Okay. And hydrogen bonds aren't very strong. Okay. We've already said they're a weak bond. They form, break, and reform easily, but they're not going to suspend liters of water inside the trunk of a tree. Okay, so how big do you suppose the tubes are that are inside the trunk of a tree that transport water? Really small. They're microscopic, in fact. Okay, there's thousands to millions of them, okay? But they have to be really small, right? If they were even, let's say, the size of a drinking straw, right, they would not be able to work because you'd have so much water, okay, inside the middle of the straw that isn't supported by anything. Okay? Water can hydrogen bond to the inside of the straw, okay, or the tubes in the tree. It can hydrogen bond to itself, but in the middle of that straw is a lot of fluid that has got nothing to hang on to, okay? And the hydrogen bonds wouldn't be strong enough to support it. Right? So what plants do is they make lots and lots of really, really small microscopic tubes. Okay? That way, the water in each tube isn't all that heavy, and there's lots of surface area for the water molecules to hydrogen bond to. So they hydrogen bond to the inside of these tubes while they're being drawn up. And they hydrogen bond to each other. So it ends up being, if you ever played with like a barrel of monkeys when you were a kid, right? You interlock the hands of the monkeys and you can pick up a whole bunch of them. That's what kind of the water molecules would look like if you could see them in the inside of the tree. Okay? They'd be stuck to the side of the tree, but also stuck to each other, okay? And that's how they would suspend themselves so that they wouldn't fall back down. Okay, okay, if the water freezes inside the tree, the water expands, breaks the tree. Okay? Which is why trees typically use length of day to cue their dormancy, right? I mean, plants don't rely on temperature to lose their leaves. They rely on the fact that days are getting shorter, they're carrying out less photosynthesis, okay? Plants have evolved to know that that's going to mean it's going to get cold soon, right? So that's what cues them to lose their leaves. When they lose their leaves, they stop carrying out photosynthesis and no water gets transported. So before it gets really cold, the water's already out of the tree, down in the roots, down in the soil. Okay. There's also usually salts and things like that that are in that water in the tree, and that can lower the freezing point, usually enough that that doesn't happen. If you get a really cold snap, it can. Okay, so that's why plants typically don't just shatter, okay, in the wintertime, because they usually don't have any water in them at that point. Okay, what does water do when you get it really hot? Boils. Does it expand then? Well, it turns into steam and it expands. You ever seen a tree struck by lightning? They explode. Okay, they explode. It's like someone threw a grenade inside the tree and just let it go off. Okay, pieces of tree fly everywhere. Okay, I've been around several trees that have been struck by lightning because I used to work at a golf course. Okay? And man, like it is scary. Okay, you see chunks of shrapnel just going everywhere. Okay, and the tree is just shattered. Right, because what happens is when the lightning strikes the tree, it superheats the water inside, and the water boils. Right? It tries to expand, but the tree's tubes won't let it, and eventually the tree just explodes outwards. Okay? Yeah, it's pretty crazy. Okay? It's also startling because you're very close to the lightning, and the thunder is very loud, okay, and follows immediately the lightning crash. Right? All right. So inside the tree trunk, okay, we can see here that we've got cohesion. Okay, cohesion means a hydrogen bond between two water molecules. Okay, and then there's adhesion, and that is a hydrogen bond between a water molecule and something else. In this case, the inside of the tree. Right? Those two processes are essentially chemically identical. It's a hydrogen bond. Okay, but those are the processes that allow water to stay suspended inside the trunk. So you can see kind of the diagram here showing these tubes must be pretty small if the water molecules, can barely fit, two side by side within the tube, right? So they're very, very small, okay? And that means you don't have a lot of weight in each tube that needs to be supported, right? What causes the water to move up the plant is something we'll talk about in the biology unit, okay? But it has to do with when water evaporates, it's still hydrogen bonded to the liquid, so as it moves out, it pulls the liquid up, okay? And then the hydrogen bond kind of breaks, and the vapor goes into the air, and the liquid moves up, okay? So it creates kind of a pulling force. Okay, so does that make sense? Okay, so cohesion, that's an important term, okay? Got to know what cohesion is, okay? Due to hydrogen bonding, okay, contributes to the transport of water, okay, so. All right, and then we've got adhesion, okay, and that is when water hydrogen bonds to something else, or two polar molecules that are different adhere to each other. Okay, and that gives the kind of droplet effect that you see sometimes on the surface of leaves, or if someone has just waxed their car or truck, okay, the rain hits it and it beads and then runs off instead of forming a sheet, okay, on there. Okay, the wax is a polar molecule, okay, water is a polar molecule, so it'll bead and adhere to the wax, okay, as opposed to just make a sheet. Okay. Right, and apparently you can do this. I've never been able to pull it off, but apparently there's enough surface tension that if you're really careful, you can actually set a paper clip on the meniscus. Okay, that is the film, the surface film, okay, of water. No, this is in a glass of water, like in a glass. Okay, and if you fly fish, okay, like that's something that I like to do. Okay, you're having a fly that you make float on the surface is entirely dependent on the surface film and the polar nature of water. Don't break the film and the fly stays on the top, okay, and doesn't sink. If you smack the fly down onto the water, it breaks the surface film and it'll get waterlogged and sink. Okay, so we rely on that surface film quite a bit, okay, for certain things, and lots of insects naturally rely on it as part of their life cycle. They need to be on the surface of the water to lay their eggs, okay, things like that, because they lay them in the water, right, and they can't sink into the water when they're doing that. All right, so there's your water strider on the right, okay, they sit right there on the surface film, okay, the Jesus lizard, okay, that can run across the water really, really quickly, kind of relies on that as well. All right, this water, though, has to be pretty still. Okay? It can't be like running water, like rough, kind of broken up water, or rapids, things like that, because the surface tension is then already broken. There has to be surface tension there already for that to work. And it has to move really fast. If you've ever watched one of these things, they're really, really quick. Okay? Their arms and legs kind of move in this circular fashion as they're running across the water. Okay? And it does break the surface tension, but it's there long enough that it can push and move. Okay? Not something that we can do, right? Obviously, we're way too heavy to be supported by the surface tension, no matter how fast you run. Okay? I know Mythbusters tried that at one point. They tried to see how far they could run on the surface tension of water, and they basically just got really wet. Yeah, and they proved also that you could do the cannonball run stunt. Okay, in this terrible movie called The Cannonball Run, they skipped a Lamborghini across like a small pond. Okay, so they came running at it, and they jumped kind of where the road ended, and they hit the water, and the car literally skipped like a rock off the water and over to the other side, which could happen provided you hit the water flat. Because I mean, when you try and skip a rock, you always use a flat rock. Well, the bottom of a Lamborghini, in this case, it was a Countach, the old kind from the 80s. Okay, it has a very flat bottom, and the engine is in the middle of the car, so it doesn't tip one way or the other, so it actually hit flat and popped over to the other side. Okay, they tried to do it with a front engine car, and as soon as they would jump, the front engine would head down and into the water. Okay, but when they distributed the weight properly, they were actually able to skip it across the water. Okay, so surface tension, if you do it right, can have quite a bit of strength. Okay, I'm not saying you should go out and try and skip across the river in your car. That's not going to work out well for you. Okay, the river is broken water and frozen right now. Okay, so it won't. Well, actually, frozen, you might be able to get across. Maybe. Don't try though. All right, so that's it for polar nature of water stuff there. Okay, be sure you understand what is meant by a polar molecule. Be sure to explain probably about the tree and how it uses cohesion and adhesion, okay, in order to survive, because those are the kind of things I'm going to ask. What does it mean to be a polar molecule, and what are some actions or repercussions of being polar that you are familiar with? Okay, those will be the things that will be asked. Okay.